Okay, so yesterday we did some more naming and writing formulas, okay, just kind of a bit of review of that. And then we talked about lab report expectations, because obviously we're going to be doing a lab on Thursday of next week, okay, but we're doing the pre-lab on Tuesday of next week. And what we go over today is what the lab is about, okay? The lab we're going to be doing next week, what you're going to do in that lab is you are going to identify 11 unknown compounds based solely on their physical properties. Okay, so what we go over today will be physical properties of various types of compounds, and what we learned today can be used to help you when you're trying to identify those unknowns after we do our various tests that we're going to do on them in order to get those physical properties. Okay, so the way it'll be set up is something like this. At the front counter, there will be the 11 unknowns, and they'll be in little beakers. Okay, and they'll be labeled A through K, right? And what you will have to do, okay, is first come up and kind of have a look at them and record what we would call observable properties. Things like color, okay, which is a physical property, okay? Nature, so is it like crystalline, or is it waxy, or is it molten, okay? Those kind of things. State, is it a solid or a liquid? Obviously there won't be any gases, they're very hard to contain in a beaker. Okay, but like those kind of things would be the things you would record. If it has a smell, okay, odor is a physical property, right? All of that stuff would be things you could readily observe. After that, you'll put a little sample in a depression plate, which I'll show you on Tuesday, okay? And you'll do like a solubility test to see how well it dissolves, okay? You will do a conductivity test of the solution to see if it conducts electricity. That can tell you something about it. And finally, you will do a pH test, okay, where you see whether it's acidic or basic or nearly neutral, right? Based on those properties, you should be able to tell me what each one of the things are. Oh, by the way, I forgot to tell you, you will have a list of the possible identities. It's not like you're going to have to pull them out of a hat, okay? So there'll be a list of, these are the things that are in those jars. You got to figure out, is A, water? Is B, hydrochloric acid? Is C, sodium hydroxide? Okay, and so on and so on. That will be your job throughout the lab. That sort of makes sense? Okay, so what we go over today will be, well, crucial for you to be able to do that on Thursday of next week. Okay? So we're going to learn the properties of compounds, acids, bases, ionic, molecular, okay? And we're going to learn how those properties can be used to identify a compound, okay? Which again will be helpful when we're talking about our lab design. Okay, so we already know that all matter is made of atoms and that all those atoms are different. Okay, they have different numbers of protons, okay, and different numbers of neutrons and all that. It's the number of protons that determine the properties of a particular element. Well, when you combine two elements in a compound, the number of protons combined still determines the physical and chemical properties of that compound. Okay? So all matter has these properties. Some are chemical, like reactivity. Okay? We're not going to be dealing with chemical properties. Okay? And some are physical, like the things we mentioned before: color, density, melting point, okay? Solubility, aqueous conductivity, pH, magnetism, okay, all those kinds of things. Okay, those properties can be used to distinguish between ionic and molecular, but also down to okay, this compound is this and this compound is this. Okay. All right. So here's what we need to know about ionic compounds. Ionic compounds exist as crystalline solids at room temperature. Okay. There are very few exceptions to that. Okay? They are typically crystalline solids at room temperature. Ionic compounds have very high melting points. Okay? We are talking several hundred degrees before ionic compounds typically melt. Okay? So does that mean that if you saw any crystalline solid, that it has to be ionic? No. Okay? Ionic compounds are crystalline solids at room temperature, but not all crystalline solids are ionic compounds. There are some things that are not. Sugar, for example. Okay. Sugar is a crystalline solid at room temperature, but it's molecular. Okay. Salt, on the other hand, is ionic and is a crystalline solid at room temperature. Okay. Now, this one is super important because it is this property of ionic compounds that will allow you to unequivocally tell the difference between an ionic compound and a molecular compound. Molecular compounds do not conduct electricity in solution. So if I dissolve sugar in water, that solution will not conduct electricity. But if I dissolve salt in water, it will. Because salt is ionic and sugar is not. So, in the lab on Thursday, if you're looking at two different white crystalline solids, and you can't do a taste test, which by the way you can't, okay, this would be the way you would tell sugar from salt. Would you agree? I mean, if you know a lot about cooking and you've used sugar and salt, a lot, you might be able to just look at them and tell the difference. Okay, they do appear slightly different, but otherwise, neither one of them really has a smell. Okay, and as we said already, they're both white crystalline solids at room temperature. The only thing that they would do differently would be conduct electricity. They even have similar pHs. Okay, that sort of makes sense? Okay. So they all conduct electricity when they're in solution, and that's because of that thing we learned about last week. Okay, when the ionic bond, remember we said, is really weak. And so when ionic compounds dissolve in water, which they typically do, okay, they separate into the negatively charged non-metal ions, okay, and the positively charged metal ions. When you have charged particles floating around in a solution, the solution will conduct electricity. Okay? If you don't have charged particles floating around in the solution, it won't. This is why distilled water doesn't conduct electricity, but tap water does. What's the difference between tap water and distilled water?
Like the minerals in water?
Exactly. Distilled water is from distilling water. So basically they evaporate water and then recondense it. By doing that, you leave all the minerals behind, and what you have is pure H2O. Okay? Tap water is not pure water. I mean, it's, typically tastes good. We're lucky in Okotoks, our water's pretty good here. Okay? But it's got minerals in it because we take it from wells. Okay? And those wells, well, they're rock. Okay? And the rocks that are in there, they've got minerals in them. Okay? The water's been in there for a long time. It's absorbed a lot of those minerals. Okay? And as a result, there's a lot of stuff in our tap water. Okay? In fact, it's the minerals that give it taste. If you've ever drank distilled water, it tastes funny. Okay? Because that's what actual water tastes like. Okay? It's actually the minerals in water, tap water, that give it its taste. That's why water tastes different everywhere you go. Okay? I don't know if you guys have ever really lived in a lot of different places. I have. Okay? And I can tell you for sure, water tastes different in every town you go to. Okay? Because they get their water from a different well or a different source, and it's got different minerals in it. Okay? Making sense? All right. Now, a couple of other things we want to know about ionic compounds. Okay, like we said, they're all crystalline solids, and those crystals all look different. Now, it's going to be pretty hard for us to look at the crystals and see what they look like because we would need a microscope to do that, and we're not going to take that amount of time. The shape of the crystals is not really important for what we're doing. Okay? But each ionic compound makes different shaped crystals. Okay, this is what I was talking about here as to why tap water conducts electricity, but distilled water doesn't. Okay, when you put salt in water, so this would be the salt here, the green and yellow stuff, okay, it breaks up into sodium, positively charged sodium ions, negatively charged chlorine ions, and now it will conduct electricity. Okay. Incidentally, if you have lots of minerals in your water, how do we describe that water? We say that water is, we have this kind of water here. Hard. You guys heard that expression before? Okay, very hard water. Maybe you have a water softener in your house. Okay, we do. Okay, hard water means typically you have a lot of calcium in the water. Okay, our water does have a lot of calcium in it. That makes it hard. Okay, that's why if your parents make you go clean your bathroom, your shower gets that soap scum on it. A lot of that is because of all the calcium in the water. Okay, if you have a water softener, your suds last longer, and you have less problem with hard water buildup on stuff. Okay, another thing, some metals make different colored salts. Okay, ionic compounds are typically called salts. Okay, that's why you'll very rarely hear me refer to table salt as salt. Okay, salt is a general term referring to any ionic compound. Okay, so all ionic compounds are considered to be salts. Okay, some of them are brightly colored or have different colors because of the metal in them. Okay, we're going to be looking at 3 in particular. Okay, nickel is one of them. Nickel always makes green salts. Okay, so if I'm looking at all the unknowns on the front table and I see one that's green and none of the others are green, and one of my unknowns is nickel 2 nitrate, is that probably that one? Okay, probably. Would I still run the other tests? I'd still run the other tests. Okay, but I'd have a pretty good idea. That one's green. It's the only one that's green. That one's probably the one that's nickel. Okay? All right, now the other 2 are copper. Copper always makes blue salts. Okay, and that's up here. Okay, so copper compounds make blue salts, and as we said already, nickel compounds make green salts, and cobalt, well, it's got a bit of a range, okay, but it's generally red, pink, and sometimes a little like rusty orange. Okay, I made the stuff up yesterday, and I think the nickel had oxidized a little bit. It's a little more rusty orange than it usually is. Usually it's actually a blood red. Okay, but I think it oxidized. I think the lid wasn't on very tight. Okay. So it's a little bit more on the orange side, but they can be anywhere from orange to red to pink. Okay. Those are typically the colors. Sometimes iron-containing salts will also appear a bit orange, but there aren't any iron-containing salts in our list of unknowns for this lab. Okay, will that be useful in identifying some of your unknowns? Yeah, definitely. Okay, so for ionic compounds, typically, ionic compounds are crystalline solids. Okay, they are also typically going to have very high melting points, so they're going to be solid at room temperature. Okay, they're also highly soluble in water, most of them. Okay, so most of your ionic compounds will dissolve pretty easily. Okay, when they do dissolve, their solutions will conduct electricity, and then we know these 3 metals in particular make ionic compounds with particular colors. Okay, everybody all right with that? Now, molecular compounds work a lot differently. We already know that the molecular bond is a very strong one. Okay, they're not trading electrons, they're sharing them. Okay, this makes them behave quite a bit differently. One of the different behaviors is that they have a very wide range of melting and boiling points. They can exist at any state at room temperature. Some of them will be solids, like sugar. Some of them will be liquids, like water. Okay? And some of them will be gases, like carbon dioxide, at room temperature. Okay? Molecular compounds can have a very wide range of melting and boiling points. Okay? They are more typically softer solids. They don't necessarily have to be. Okay? Obviously, we said sugar is a crystalline solid, okay? But most of your molecular compounds will be softer, okay, as a solid. So think of like butter, okay, or candle wax, okay? Like as opposed to crystalline candle wax, you can flake it with your fingernail, right? If you run your finger up the side of a candle, it'll flake off, okay? Butter, if you do that, well, it'll get all smeary, okay? But we get a much different type of appearance to them, okay? Also with molecular compounds, you don't typically get any bright colors, okay? They might have a color, but it's not gonna be bright like the nickel and the cobalt and the copper. Okay, so solids, liquids, or gases at room temperature. So, if one of your unknowns is a liquid, can you eliminate all the unknowns that are ionic from your list? Okay, so if I'm looking at, let's say, compound J in my unknowns on Thursday, and I see that it's a clear liquid, I know that it isn't any of the ionic compounds on my list. I know it's not nickel 2 chloride. I know it's not copper 2 sulfate. Okay, I know it's not ammonium nitrate or any of those things because those are all ionic compounds and they're crystalline solids at room temperature. Okay, so seeing something that's a liquid really eliminates a lot of possibilities for its identity on the list. Okay. Okay, molecular compounds are not usually as soluble as their ionic counterparts. Even something like sugar that we typically would associate with being quite soluble is not as soluble as salt. Okay, I mean, you know this, if you've ever tried to make drinks from a powder, okay, so if you've ever got like the Gatorade powder, or the BioSteel powder, or even if you ever make Kool-Aid, okay, the way I used to make that stuff is I would actually make it with warm water, and then I would pour all the stuff in and shake it up, stir it up. Why would I use warm water? It dissolves faster and dissolves more. Okay? Then I put it in the fridge. And after a while, I'd see a thin layer of sugar form at the bottom. Then I knew it was good. Okay? Because I knew it was saturated. It couldn't possibly dissolve any more sugar. Okay? And so it would be super, super sweet because that had a bit of a sweet tooth. Okay? And so that's how I would make it. Okay? I obviously wouldn't drink it when the water was warm. I just made it with warm water because I could dissolve sugar. Okay? All right. The other thing is because of the nature of the bond, okay, in that electrons are not being traded, they're being shared, they won't break up into charged particles when they dissolve, which means molecular compounds will have solutions that don't conduct electricity. We already said that's how you'll separate salt from sugar. Okay? Sugar is a molecular compound. Okay? It's like C12H22 something or other. Okay? Dextrose. Yes. Okay? So that's one of the ways we can tell them apart. Okay? But yeah, they typically won't dissolve as easily or maybe at all. Okay? And last time I checked, if you dunk a candle in water, it doesn't dissolve. Okay? Paraffin is a molecular compound. Okay? Questions there? All right. Okay, molecular compounds which are soluble in water typically produce clear solutions, so you're not going to get anything brightly colored when it does dissolve. Okay, and as we said, those won't conduct electricity. Now, acids and bases. Okay, by definition, anything with a pH lower than 7 is an acid. Anything with a pH higher than 7 is a base. Okay, but lots of things are below 7. And we wouldn't necessarily consider them acidic, okay? Like, I mean, rain can have a pH as low as 4, okay? But we don't consider that acidic. Like, we don't worry about it dissolving our skin when it falls on us, okay? But it can have that low of a pH. So what we're going to be talking about in our lab are strong acids and strong bases. These would be things that if their acids have a pH lower than 2, okay? Or if they're a base, have a pH higher than 12, okay? So we're talking like strongly basic or strongly acidic, okay? Because even something like lemon juice is acidic. It has citric acid in it, okay? But we don't consider it necessarily a strong acid because we can drink that stuff, okay? It's not going to hurt us, right? Even inside your stomach, there's acid, okay? It's ionic, but it's an acid. Okay? All right, so acids are compounds that typically have H plus ions in them. So acids are ionic compounds where hydrogen is acting as the metal. Okay, so if one of your unknowns starts with H and it isn't water, okay, it's probably going to be acidic. Okay, I'll give you an example. What's that stuff? Hydrogen chloride, okay, as an acid, hydrochloric acid. It's the acid that's in your stomach. Okay, the pH of your stomach is about 2. Okay, it's helpful for breaking down proteins and fats and things like that. Okay, it's why you have to have the lining around the inside of your stomach, which is made of mucus. Okay, the inside, your stomach cells, the stomach lining cells, secrete this mucus layer that protects your stomach lining from the acidic hydrochloric acid. Okay, if something is interfering with the production of that mucus, you can get an ulcer. Okay? An ulcer is basically a chemical burn on the inside of your stomach. Okay? Or even the upper part of your small intestine. You can also get a duodenal ulcer, okay? Which is an ulcer of the duodenum, which is the first part of your intestine that connects to the stomach. It's a very common place, actually, to get an ulcer. Okay? Because if it's not well protected, okay, those acids can burn a hole in it. Okay? Now, I'm not saying like burn a hole, like literally stomach acids leaking out of your stomach, although that can happen, but it's extreme. Okay? But you can get little chemical burn lesions on the inside of your stomach, and that can be caused by any number of things. High anxiety can cause interference with how the stomach lining produces mucus. Alcoholism, okay? Alcohol tends to dissolve the lining of the stomach, okay? And can cause ulcers. So people that are alcoholics regularly or highly intoxicated will often develop ulcers, okay? Things like that. Okay, acid reflux is another one. If you have really bad acid reflux, your stomach acid comes up into your esophagus, and you can get an esophageal ulcer, because your esophagus is not lined like your stomach is. Okay? How many people have ever had heartburn before? Okay? Heartburn is from acid reflux. Some of your stomach acid has actually made its way past the esophageal sphincter. That's the muscle that basically is supposed to keep it all inside there. Okay? If it gets past there, okay, then it starts to burn the inside of your esophagus. If you've ever vomited, that's the sensation you get. Okay, that burning sensation, that's your stomach acid. Okay, so acids are ionic compounds, thus share many of their properties, crystalline solids, highly soluble in water, okay, and they will be your best conductors of electricity when in solution. Okay, because acids containing hydrogen as the metal break up the most easily of any type of ionic compound. Okay, so they're the ones that produce the most amount of like hydrogen ions and whatever else is attached to it. Okay, hydrochloric acid is not the only acid. Okay, in fact, it's not the strongest acid either. Right? You can get hydrogen iodide, also an acid. Okay? Anything that starts with hydrogen as the metal is going to be an acid. Which would be stronger? Whoa. This, hydrochloric acid, or this, sulfuric? Which would be stronger, do you think? Let me tell you this piece of information. The more hydrogen ions a solution has in it, the more acidic it will be. Yeah, sulfuric acid will be more acidic. It has 2 hydrogen atoms in it. Okay? So when it breaks up, it's going to put 2 hydrogen atoms or ions into the solution versus only 1 for the hydrochloric. Okay? This stuff here, okay, is very dangerous. In fact, if you work in oil and gas, especially if you're on the rigs, okay, you have to take a safety course, an H2S Safety course. This gas is often associated with the extraction, okay, of oil and gas. Right? If it leaks out, okay, and it's inhaled, it burns your lungs. Okay? It's very, very dangerous stuff. Okay? That's why you have to take the safety course, have all the right gear, okay, the mask and the respirator and all that stuff. Okay, and what about this stuff? Would that be even more acidic? Nitric acid? Okay, very, very acidic stuff. Okay, in fact, you have to be careful not to get the fumes on you from that stuff. Okay, if you have the container of it open and you have your hands over top of the container, you'll have chemical burns, quite deep tissue ones, okay, on your hands within an hour. Okay, and deep tissue, we're talking at least 2nd degree chemical burns, okay, from that stuff. Very dangerous stuff. We don't play with that. We don't have any even. Okay? This we got lots of. We even have some of that. Okay? All right. Acids taste sour. Should you do a taste test of any of the unknown compounds? You should not. Okay? I made the stuff yesterday. Okay? The hydrochloric acid is uber concentrated. I just like my stuff to work. Okay? So when we do a lab, I like to get really good, obvious results. It's about half and half water and acid. Okay? If you do a taste test of that, it will be the last thing you taste. Okay? And not because you'll die, but because you'll burn your tongue off. Okay? So yeah, don't want to do that. Okay? But typically, acids are tart or sour. Okay? So citric acid, right? Tastes sour. Vinegar is tart. Okay? It's an acid as well. Okay, and like we said, acids typically have a low pH, so less than 7, and our strong acids are less than 2. Okay, so does that mean we have to treat all of the unknowns with a great deal of care and respect? Okay, when we're doing the odor test, okay, when we're up at the front and we're, trying to get the smell of the compounds, okay, how should we do that? Should you like put your, pick it up, put your face right over, put your nose inside the beaker, go, don't. Okay, you definitely do not want to snort any of these compounds. Okay, the hydrochloric acid, if you do that over top of it, you'll be flat on your back. Okay, I actually had this happen to me one time when I was a very young, new teacher. I was making some hydrochloric acid for a lab, and I had a cold, and I sneezed right over top of the open container. And what do you do right after you sneeze? You strongly inhale. Well, I strongly inhaled, flat on my back. My colleague was like freaked right out when they came in and saw me. I had blood coming out of my nose. Okay, it was gross. Okay. So you definitely don't want to snort any of these. How do you properly smell something? What do we call that? Starts with a W. Wafting. Okay? You want to waft them. If any of them have a smell that's important, you'll smell it. Okay? If you're going like this, like I don't smell anything, then it doesn't have a smell. Okay? Because I see people like, pretty soon their nose is inside the container. If you don't smell it from doing this, it doesn't have a smell. Oh, by the way, make sure you don't send up the guy who's hard of smelling, okay, to do that test. Okay? Or the guy with a cold. Okay? Don't send them up to do the smelling. Okay? Because I've had groups do that. Person comes up and they're like literally leaking mucus all over the place. My group sent me up. It's great. Like, send somebody else and go home. You're sick. Okay? All right. So those are acids. Okay? Now bases are the ones that have the high pH. Okay? And bases always have hydroxide in them. Okay? They're always ionic compounds. Strong acids. Sorry, strong bases are always ionic compounds. And those ionic compounds will have hydroxide acting as the non-metal. Okay, so their solutions are going to conduct electricity, just like acids, very, very well. Okay, our conductivity testers have a scale from 1 to 10. The strong base and the strong acid will both read 10. Okay, they'll be extraordinarily good at conducting electricity. Okay? Typically bases taste bitter. Again, we're not going to be tasting any, okay? But something like baking soda is bitter. Salt, or sorry, not salt, soap, okay? It has lye in it. Lye is bitter, okay? So bases typically taste bitter, okay? And they'll turn your litmus indicators blue. We will have not litmus paper, but what we call hydrion paper, and it actually turns a different color for every level on the pH scale. Okay, so like really bright red, that's a 1. Okay, you know, less bright red, it's like a 2. Orange, okay, green, all the way up to like basically black for 14. Okay. All right, so we said they have OH ions in them. That's hydroxide, and that is the basic ion, the thing that makes things basic. Okay, so if I had this stuff, NaOH, is that a strong base? It is. That's the stuff that's in oven cleaner, okay, or grill cleaner or whatever. Okay, you spray it on, foams up. Okay, that's sodium hydroxide. Okay, very strong base. It's one of your unknowns in the lab. Okay, so you'll have to look for a strong base for that one. Okay, what about this stuff? Would that be stronger or weaker than the first one? Be stronger. Just like acids, the more OH you have, the stronger the base will be. Okay. All right, so if you have an ionic compound in the unknowns and it ends in OH, okay, should it be basic? Should it come up with a high pH? It should. Okay, what if I had this stuff? Would that be a strong base? It ends in OH, but is it an ionic compound? It's not. Okay, because it starts with a non-metal, right? It starts with carbon, which is a non-metal, right? That is ethyl alcohol, right? It's what's in booze and hand sanitizer, okay? It's definitely not a strong base, okay? So it has to be an ionic compound that ends in OH for it to be a strong base, okay? Just don't want anyone to get confused. All right. Okay, that's all we need for the properties of compounds, okay? On Monday, we'll start talking about some of the tests that we're going to run, and then Tuesday we have the Chromebooks, okay, to work on the pre-lab stuff. Okay, so figured we'd have a little bit of time to do this stuff. Okay, so I would like you guys to give me the names for the circled compounds there on the list, please. So for number 1, okay, we got nitrogen and chlorine, ionic or molecular? Molecular, that's 2 nonmetals. Okay, so do I need prefixes? Okay, what prefix needs to go on nitrogen? Di. So we have dinitrogen. Okay, and what goes on the chlorine? Tri. And we end in ide. Okay, I had a good question about where do I put the ide ending? Like, is everything on the, some of them end in ene, some of them end in eum, and some of them end in ogen or igen. Okay, you kind of have to go by feel a little bit, except for anything like chlorine or bromine or iodine. Okay, you just replace the N with a D, and you're good. You've got it ending in ide. Okay, for something like oxygen or nitrogen, okay, you basically take out the ogen or igen and you put the ide there. Okay, if it ends in eum, you got choices. Okay, like selenium, we said could be selenide or selenamide. Okay, tellurium is usually telluride. Okay, you just have to kind of go by where does it make the most sense, where does it sound right, okay, to put that I ending. Okay, like I said, everything in group 17 is pretty obvious where to put it, okay, but for the other ones, it's not as obvious, so you kind of just have to go with, well, in the English language, which one is going to sound right, okay, and you're probably good. Okay, for number 2, okay, we've got iron and nitrogen, ionic or molecular? Ionic, is it going to need a Roman numeral? Yes, iron's got more than one possible charge. So the first thing we'll do is we'll write iron nitride, because we know that's how it's going to go. Okay, we just have to figure out which Roman numeral. Well, nitrogen's always a -3. Since there's one nitrogen and one iron, what does the charge on iron have to be? +3. Yeah. Okay, and for number 3, we got calcium and sulfate, ionic or molecular? What do you think? Ionic. Calcium's a metal, and we have a polyatomic ion. Okay, so calcium, we write the name of the metal. Okay, then we write the name of the nonmetal. In this case, a polyatomic ion, whose name I write just like the chart, calcium sulfate. All right, and then for number 4, okay, we got another ionic compound. Okay, beryllium with bromine, so that'll be beryllium. 2 L's. Beryllium bromide. Okay, and then for number 7, going to need a Roman numeral in this ionic compound because cobalt has more than one possible charge. So we'll go with cobalt, okay, and nitrate. Okay, since nitrate's always a -1 and there are 2 of them, that means there's 2 negative charges. Since there's only 1 cobalt to balance that, it must be the +2 variety. Okay, and then number 9, molecular compound, they're both nonmetals. Okay, phosphorus doesn't need a prefix because there's only 1. Okay, and then trioxide. Okay, questions on those? Okay, have you do a few that go the other way before the bell goes here. All right, let's look at those 5. All right, so our first one here, we got iron 2 hydroxide. So it's an ionic compound. We write the symbol Fe. The Roman numeral tells me what charge to use. And it's with a polyatomic ion, OH, which has a -1 charge. So when I drop and swap, I'm going to be looking at Fe, OH in brackets 2. Okay, and then for number 43, we have another ionic compound. So I write the metal, aluminum, with its charge, 3+, and it is with nitrogen, which is a 3-. So those already balance out. So it would be Aln for that one. All right, and then for potassium phosphide, okay, we would have K, it's a +1. Phosphorus, it's a -3. So when we drop and swap, we get K3P. And then we got a molecular one here, diphosphorus hexachloride, P2Cl6. Do I reduce that? No, because it's molecular. We don't reduce the molecular ones. All right, and then the last one, tungsten oxide. Tungsten is W, and it has a +6 charge. Oxygen's a -2. When we drop and swap, we're going to get 2 and 6. What do I do with those 2 numbers? Those ones I would reduce to 1 and 3. Okay, so next week, we're starting the stuff for the lab. Okay, probably talking about solubility a bit on Monday. Okay, Tuesday's quiz will be on naming and properties of compounds, the stuff we went over today. Have a good weekend, but not too good.